Even though some are not as obvious as these, chemical reactions are the reason our bodies work. They break down our food, build up our muscles. Chemical reactions even make us feel the way we do, happy or sad, warm or cold. The final reaction occurs when sugar and sulfuric acid are mixed. It produces heat in a tall column of pure carbon. Chemical reactions change one set of chemicals into another. The reactants are the substances that you start with. The process of burning is a chemical reaction. It requires the substance being burned as well as oxygen. These are the reactants. Once you add heat to get the reaction going, the substance you started out with changes, transforms into the products. Burning something like rocket fuel always produces two products, carbon dioxide and water. Because the fire makes things so hot, the water is usually in the form of steam. The combinations of steam mixed with carbon dioxide gas give smoke its characteristic smell and haziness. Depending on what you're burning, there can be other substances left over as well. For example, the ash produced when you burn paper. A chemical equation is a shorthand way to represent a chemical reaction. It's written almost like a timeline. First is the chemical symbols for the reactants, then an arrow which represents the transformation, and finally the chemical symbols for the products are written. The arrow in the chemical reaction is read as yields. So this reaction, which is the chemical reaction that occurred when the atomic bomb was dropped, would be read hydrogen and oxygen yield water. Sometimes energy is a product of a reaction. It was obviously one when the atomic bomb was dropped, but since it's not a chemical, it's not written into the chemical equation. You probably learned in junior high physical science that matter cannot be created or destroyed. So then where did the water in the reaction come from? What's actually happening during the chemical reaction is that chemical bonds are being broken and reformed between different atoms. Methane is one of the main components of natural gas used to heat our homes. Your burns it in the presence of oxygen to produce carbon dioxide and water. If you count the numbers of each atom before and after the reaction, they're equal. One carbon on each side of the reaction, 4 oxygen, and 4 hydrogen. They're just combined into different compounds before and after the reaction takes place. The breaking and reforming of bonds requires energy. Energy is stored in chemical bonds, and when they're broken, the energy is released. When new bonds are formed, the energy is absorbed. Chemical reactions recycle this energy so that the energy produced breaking the bonds in the reactants is used to form the products. However, very rarely is the exact same amount of energy stored in the bonds of the products as there is in the reactants. Therefore, some chemical reactions produce heat if breaking the bonds of the reactants produces more energy than the products need to form, and other reactions absorb heat from the environment if the bonds of the products require more energy to form than the reactants provided. The chemical reaction that produces fireworks releases heat as it occurs because bonds in the reactants have more energy. The chemical reaction between baking soda and vinegar, on the other hand, require more energy than the reactants can provide, so they absorb energy from the environment. These are graphical representations of two reactions. The first shows the reactants not having very much energy, but the products storing a lot of energy. This means the reaction must absorb heat from the surroundings in order to form the bonds in the products. In the second reaction, the reactants have more energy than the products, so the energy is being released when the bonds are broken. The activation energy is the energy needed to get a chemical reaction started. Sometimes chemical reactions can get this energy from the heat in the environment, but many times the reaction requires more energy than the environment can provide. For example, fireworks don't go off spontaneously, even if they're sitting outside on a hot summer night. You must light the fuse to give the reactants enough energy to begin changing into the products. The energy required to do this is called the activation energy. Chemical reactions that take place inside of living cells require energy too. Instead of lighting fuses inside of your cells, Your body uses substances called catalysts to lower the amount of energy needed to get a reaction started. The result is that the rate at which the chemical reaction takes place speeds up. This graph shows how energy in a chemical reaction changes as the result of a catalyst. The black line shows how much energy is needed to get the reaction started without a catalyst. The reaction must absorb a lot of energy from its surroundings in order to get started. Because each molecule of reactant needs this much energy, the reaction might happen very slowly or not at all. However, when a catalyst is present, the amount of activation energy is lowered. Now it might be possible for many molecules of reactants to proceed with the reaction because they're able to absorb that energy from their surroundings. Can you see now why it might be dangerous to have a high fever? You might be providing too much energy to chemical reactions, and so they proceed too quickly. Another danger is that at high temperatures, proteins lose their three-dimensional shape, and so they don't work properly. If this happens, we say that the protein is denatured. Enzymes are proteins that act as biological catalysts. So a catalyst is a molecule that makes any chemical reaction speed up, and an enzyme is a catalyst that speeds up a reaction in a living organism. Enzymes are very specific due to their shape. Therefore, they're only able to catalyze one specific chemical reaction. The reason they're so specific is because the reactants physically fit into an enzyme like a key fits into a lock. Enzymes have an active site that allows the reactant to bind to it. When an enzyme is used in a chemical reaction, the reactants are called substrates. So when an enzyme is used in a reaction, first all the substrates bind to the enzyme at the active site. The bonds of the reactants break, and new bonds form in the products. The products are then released from the active site, and the enzyme is free to catalyze the next reaction. The next 3 slides show a real example of how this happens. It's the first step in the process of breaking down glucose. See if you can describe what's going on. Three things can affect how fast enzymes work in cells. Chemical reactions only happen at certain small ranges of pH values. That's why buffers are so important in cells. Temperature can also affect how fast enzymes work by denaturing the enzyme or changing its shape just enough so that the substrate doesn't fit into the active site. Finally, other molecules can affect the speed of a chemical reaction. Another substance may block the active site so that the substrate cannot bind. This is a common way that cells regulate the rate of chemical reactions in a cell. The cell will produce something that blocks the enzyme when it doesn't want the reaction to happen, and it may produce something to destroy that molecule to make the active site available again when it needs the reaction to proceed.